Okay, everyone, I hope you're enjoying these shorter lectures. Maybe you can catch one in between, I don't know, in the morning when you wake up before you do anything really important. At any rate, here's the next section, aqueous solutions or aqueous solutions. Some people say aqueous, some people say aqueous. I don't think it really matters, but I suppose aqueous would be better because when you say aqueous, that's kind of like Aquaman, and Aquaman has a AQUA. So clearly this is aqueous. I don't care. Explain the difference between electrolytes and non-electrolytes and recognize examples of each. Predict the solubility of ionic compounds in water. Okay. So here, if we take a look at ions and molecules in aqueous solution, the focus for this slide is on ions in aqueous solution. So if we take a look at ions in water, here's an ionic compound. This is called iron 3 oxide. And if you add water to this stuff does not dissolve. We say it does not dissociate. We also say it does not ionize. Okay, so when we say ionize, it means a special thing because there are ions in there. So what do we mean by it does not ionize and it does not dissociate? How are these the same thing? Well, let's take a look at what happens when sodium chloride has water added to it. All of the sodium ions and all of the chloride ions separate from one another and are surrounded by molecules of water. So the ions separate from one another and are surrounded by H2O molecules. And these things that dissolve, these ionic compounds that dissolve, are called strong electrolytes, which are solutions that conduct electricity. They conduct electricity due to the free-floating ions in solution, whereas this will not conduct electricity because there are no free-floating ions. So here, for a strong electrolyte, the ions dissociate completely. Now you want to do yourself a favor and Google sodium chloride dissolving in water videos, okay? You'll see a lot of good cartoons about how water will dissolve an ionic compound. So when we take a look at electrolytes in aqueous solution, these are ions in aqueous solution, they promote the conduction of electrons, which we say is conductivity, okay? So this is my version of a light bulb with a cord going to the wall. I started to make it simpler as time went on. So here is the filament in the light bulb. So this is an old light bulb, an old-timey light bulb. And when you have a strong electrolyte, if you have this light bulb in the solution, this light will light up very brightly. Examples of strong electrolytes are NaCl, which is an ionic compound that dissolves, and HCl, which is a strong acid. There are weak electrolytes. So when you put this into solution, you don't get many ions, and we'll be talking about that in a little bit. It has to do with that equilibrium type of stuff. And so when this conducts electricity, since it has fewer ions, you get a less bright light. And here, for a non-electrolyte, no ions in solution. And so here, you get no light whatsoever. And so here, no little hairs, if you will, coming off of that, meaning no light. So now let's look at ions and molecules in aqueous solution, the focus on molecules. So for molecules, you actually have strong electrolytes, weak electrolytes, and non-electrolytes. So this is a molecule, HCl. We know it's a molecule because these are all nonmetals. When you put this into water, what happens is you get these two ions. So every one of these put into water will end up producing two ions. So this makes it a pretty good electrolyte, a very strong electrolyte. So it dissociates or ionizes completely. Sometimes we like to write it this way because it's just a little simpler. Now, here's a weak electrolyte. This is a weak acid. It's called acetic acid. When you put it into water, it can form these ions, just like these ions up here. However, we have these two arrows, which means that only part of this will react and the other part won't. In fact, in this particular reaction, it is reactant favored, which means you don't have very much product, which means the conductivity will be low and it won't light up very brightly. So it dissociates or ionizes incompletely, and we can tell that from the double-headed arrow. So here are the non-electrolytes in aqueous solution. This is a molecule called glucose. It's also a molecule called fructose. You add water and the molecule dissolves. Now, the molecule does not come apart into its atoms, but rather a molecule is one structure, and all of these structures are kind of stacked one on top of another in this solid. And when you add water, those structures separate from one another. Now here I kind of wrote one of the formulas backwards to hopefully give you the idea that glucose molecules don't all float the same way. They kind of, float however. I should have written one upside down also. Okay, so there's no dissociation or ionization. These mean the same thing, so it really shouldn't be an or, it should be a slash, no dissociation, ionization. So you should come to terms with what dissociate means. It means dissociate into ions. So let's take a look here and say, what is an electrolyte? An electrolyte is a compound that dissociates into ions when dissolved in water. What I like about that is it's very succinct and it covers all the bases: dissociation, ions, water. Okay, so that's an electrolyte. And you probably have heard of electrolytes. They're very important for people. When you sweat, you lose a lot of electrolytes, and those electrolytes are essential in your health. And so that's why they invent drinks that replace those electrolytes. How can you differentiate experimentally between a weak electrolyte and a strong electrolyte? And the answer is use a light bulb. If you want to electrocute yourself, use a conductivity meter. The strong will have high conductivity, and the weak will have low conductivity. So an example, something that would be a strong electrolyte is NaCl or HCl, you've seen before. Low conductivity, the only example you've seen so far is the acetic acid. So part of this same section about aqueous solutions, we talk about the solubility of ionic compounds in water. And this is going to lead us to the first type of chemical reaction we're going to study, which is called a precipitation reaction. And there will be a precipitation lab. So let's look at the solubility of ionic compounds in water. An ionic compound is considered to be soluble in water when 10 grams of it dissolves in 100 milliliters of water. It's insoluble if less than 10 grams dissolves. It's kind of an arbitrary cutoff. So this is kind of to tell you that all ionic compounds are somewhat soluble in water, but we consider the cutoff to be around 10. So there are some guidelines for what types of ionic compounds will dissolve in water. Those with a group 1A ion. So this will dissolve because it has sodium in it. This will dissolve because it has potassium in it. Those with the ammonium ion. Those with the nitrate ion. So this will dissolve because it has the nitrate ion. With the acetate ion, the chlorate ion, and the perchlorate ion. So these, if you see any one of these in the compound, it will dissolve. That's what we're going to go with. It's not really true, but it's the easiest thing to think about. Those are clinchers. They're guarantees. These two here are things that will dissolve usually unless they're combined with something else. So halides, these usually dissolve. Iodide, chloride, bromide, except when they're combined with silver, lead, or mercury 1. Okay? So that means that AgCl, you would think would be soluble because it has the chloride ion in it, but it's not because it's also got the silver. So this is insoluble. That's the term we use for not soluble, insoluble. Most of your sulfates are soluble, except when combined with basically any monoatomic ion that has a +2 charge. And really, these are group 2A, lead 2 or silver. And then there are compounds that are not soluble. Oh, I skipped one. So here are the compounds that are not soluble. So insoluble means not soluble. So compounds that have carbonate, phosphate, this is called oxalate ion. This is the chromate ion. This is sulfide. So for example, calcium carbonate is insoluble. Why? Because it's got the carbonate. Now there are exceptions here. What are the exceptions for these? Well, if we go back here, if it's got one of these in it, it's soluble. So sodium carbonate is soluble. Why? Because it's got the exception. The exceptions are group 1A ions and the ammonium ion. Those are the exceptions. And here also, ions that have oxide or hydroxide. You know, this one I would actually put down with this list because these are similar, right? They're in the same group. So these are insoluble. So copper hydroxide, insoluble. Potassium hydroxide, soluble. Why? Because hydroxides are insoluble. But here, all potassium compounds are soluble, so it kind of wins over the hydroxide. So let's try and apply these solubility guidelines. And you might want to be looking in your book when we're doing this at first, but eventually you want to try to know these pretty well for the exam when you take exam 2. Or you might consider putting this on your note card for exam 2, but being able to use the guidelines very quickly, not having to think about them. You can just look and say, okay, here's what's happening. So here, when I take a look at this, I always look at the cation first and see if it's one of those always soluble cations in group 1A or ammonium. And here, this has got potassium in it, so this is soluble. Done deal. So I'm going to look at that cation. It's got magnesium in it. That's not a clincher. So I don't know about that. But I see that it has carbonate, and when I look at the list, carbonates are not soluble. The exceptions are when they're combined with a group 1A ion or ammonium, and that's not when a 1A ion, so this is insoluble. How about this iron hydroxide? Well, there's no rule for iron, but there is one for hydroxide. So the hydroxide ion is insoluble unless combined with sodium, potassium, lithium, or ammonium. So this is insoluble. And here we have this copper. There's no rule for copper. This is copper. Well, this should be iron 3. Did anyone catch that? Iron 3 hydroxide? This is copper 2 nitrate. And the rule for copper is there is no rule, but there is a rule for nitrates. They're soluble. So that's how you look at the formula to figure out how it's soluble. And again, you want to use those guidelines. So I'm going to show you very quickly. If we look at KCl, how do we know this is soluble? It's got a group 1A cation. How do we know that MgCO3 is insoluble? Well, because it's got a carbonate anion. How do we know that iron 3 hydroxide is insoluble? Because it's got a hydroxide anion. And how do we know that the copper 2 nitrate is soluble? And the answer is because it has the nitrate anion. You want to get used to using the guidelines and being proficient at it to save time when you're taking your exam or quiz. Okay, take a look at the next one here. Which are water soluble and which are water insoluble? So you already know that you should be hitting pause and then hitting play again after you've figured these out. So give yourself some time to figure these out and hit pause. And you're back. So I'm going to use S for soluble and I for insoluble. So how about this copper oxide? Insoluble. Copper chloride, soluble. Iron 2 carbonate, insoluble. Silver iodide, insoluble. Iodides are usually soluble unless they're combined with silver. Silver phosphate, insoluble. Phosphates are insoluble. Silver nitrate, soluble because all nitrates are soluble. Potassium carbonate, soluble because of the potassium. Potassium iodide, mostly soluble because of the potassium. Potassium permanganate, soluble because of the potassium. So if I circle the things that led me to these conclusions, they would be here the oxygen, here the chloride, here the carbonate, here the nitrate, here the phosphate, here the iodide with the silver as an exception, here the potassium, here the potassium, and here the potassium. Those were what led me to those conclusions. So sometimes it's the cation that tells you, sometimes it's the anion. Okay, the following are water soluble. What ions are produced by each compound in aqueous solution? Well, the first one, we know that the metal is a potassium ion. It's in group 1A with a +1 charge. And the rest of it must be the anion. And we recognize that as being the hydroxide ion with a -1 charge. Here we recognize that the first element is a metal atom. That's the cation. And there's 2 potassiums. And the rest of it is the anion. And of course, it's got to have a -2 charge because we've memorized it, but also we can figure it out because we know that each potassium is a +1. And all these charges here must add up to 0. So here, lithium, group 1A, +1, nitrate, NO3, -1. Here, NH4 we recognize as the ammonium ion. There's 2 of them. So this is another way to write 2 of the ions. I don't have to write them twice. I can write a 2 in front of it. And then we have the sulfate ion. So these are the ions produced by each in aqueous solution. Decide which of the following is water soluble. If soluble, tell what ions are produced when dissolved in water. So which ones are soluble and which are insoluble? This one is soluble because of the sodium. This one is soluble because of the sulfate. This one is insoluble because of the sulfide. And this one is soluble because of the bromine. So the ions in solution are 2 sodiums and 1 carbonate. Here, one copper 2, and a sulfate. I know it's a copper 2 because the sulfate has a -2. Here, we don't need to worry about the ions because it's not soluble. And here, we've got a barium ion, and we've got 2 bromide ions. Okay, and that's the end of this section. Thank you for listening.